contains two types of photoreceptors, rods and cones. Both types have an outer segment composed of membranous discs containing light-sensitive photopigments. Each also has an inner segment that contains the cell nucleus and gives rise to synaptic terminals that contact bipolar and horizontal cells. Phototransduction is the process of a cell absorbing light and creating a response. The response is a change in the amount of transmitter that is being released onto target neurons. The photopigments lie within the disc membranes of the outer segments. In rods, the photopigment is called rhodopsin. The 7 transmembrane domains of the protein portion of the molecule, called opsin, traverse the membrane bilayer. The opsin forms a pocket in which the light-absorbing portion of the photopigment, a molecule called retinal, resides. The photopigments in the rods and the 3 types of cones differ in the protein portion of the molecule, which tunes retinal to absorb specific wavelengths of light. Here, retinal is in a conformation called 11-cis, with cis referring to 2 hydrogen atoms being on the same side of an important double bond. When retinal absorbs a photon of light, a component of this double bond breaks, allowing free rotation about the bond. This change in retinal to an all-trans form triggers a series of alterations in the opsin component of the molecule. The changes in rhodopsin lead to a cascade of events in the cell. The next component of the cascade is a trimeric G protein called transducin, which in its inactive state is bound to GDP. The altered rhodopsin molecule activates transducin, allowing it to exchange its GDP for GTP. The alpha subunit of transducin then activates a phosphodiesterase in the disc membrane. Phosphodiesterase hydrolyzes cyclic GMP, thus lowering the concentration of cyclic GMP throughout the outer segment. As the concentration of cyclic GMP falls, the molecule no longer binds to and holds open ion channels in the surface of the outer segment membrane. Let's compare the action of the ion channels in the light and in the dark. In the dark, the ion channels are open. The influx of the positively charged sodium and calcium ions has a depolarizing effect on the cell. The inward current is opposed by positively charged potassium ions flowing out through potassium channels, a hyperpolarizing influence. The combined result of these ion flows, however, is the depolarization of photoreceptors in the dark. In the dark, the depolarized state of the membrane, which is at approximately -40 millivolts, triggers continual transmitter release from the synaptic terminals of the photoreceptor cells. Absorption of light reduces the concentration of cyclic GMP in the outer segment, leading to the closure of the cyclic GMP-gated channels. As a result, positive charge carried by potassium ions flows out of the cell more rapidly than positive charge carried by sodium and calcium ions flows in. The cell becomes hyperpolarized, that is, more negative, and decreases its release of transmitters. One of the important features of this cascade is that it provides enormous signal amplification. A single light-activated rhodopsin molecule can activate an estimated 800 transducin molecules. Although each transducin activates only one phosphodiesterase molecule, each phosphodiesterase is capable of breaking down as many as 6 cyclic GMP molecules, resulting in the closure of approximately 200 ion channels. This number of channels represents 2% of the number of channels in each rod that are open in the dark, and their closure causes a net change in the membrane potential of about 1 millivolt. Proteins in the photoreceptor limit the duration of this amplifying cascade and restore the various molecules to their inactivated states. Activated rhodopsin is rapidly phosphorylated by rhodopsin kinase, which permits the protein arrestin to bind to rhodopsin. Bound arrestin blocks the ability of activated rhodopsin to activate transducin, thus effectively truncating the phototransduction cascade. By hydrolyzing GTP, activated transducin has a built-in timing mechanism to turn itself off shortly after becoming activated. Without activated transducin, phosphodiesterase also turns off. Finally, through a multi-step pathway, the cell converts rhodopsin back to a form that can absorb light. Also in the dark, the enzyme guanylate cyclase again builds up the levels of cyclic GMP. Cyclic GMP opens the ion channel, allowing an influx of ions and depolarizing the cell.
So this last bit was sort of a little extra, but regarding what the cell, how it restores itself to, without depleting all of these players, it's ready again for the next signal. I also feel like I want to go back one slide and be a little bit more clear. Where am I? So let's look at that.
Visual processing begins in the retina, the receptive surface inside the back of the eye. Light enters the eye, passes through the layers of cells in the retina before reaching the photoreceptors, which are located at the back of the retina. Light activates the photoreceptors, which modulate the activity of bipolar cells. Bipolar cells, in turn, connect with ganglion cells located at the front of the retina. The axons of the ganglion cells form the optic nerve, which carries information to the brain. Two other types of neurons, horizontal cells and amacrine cells, are primarily responsible for lateral interactions within the retina. The bipolar cells and ganglion cells are organized in such a way that each cell responds to a small circular patch of photoreceptors, which defines the cell's receptive field. The receptive fields of retinal ganglion cells are concentric, consisting of a roughly circular central area and a surrounding ring. Retinal ganglion cells have two basic types of receptive fields: on-center off-surround and off-center on-surround. The center and its surround are always antagonistic and tend to cancel each other's activity. Let's look at the response of an on-center ganglion cell to a spot of light. When no light is falling on the receptive field, a spontaneous level of activity is recorded from the ganglion cell. To see what happens when a spot of light enters the receptive field.
Okay, Courtney. So we're talking about the ganglion cell being stimulated. Thank you. The photoreceptor was suppressed, was hypopolarized by light, but somewhere in the pathway that must translate
something's getting
switched.
Yeah.
Right. Something's getting switched, so the ganglion cell is getting activated by light. Thank you. Okay.
Use the mouse to position the beam of light so that it falls on either the center or surround of the receptive field.
Oh, I'm supposed to do something. There we go. So when I put it in the center, it goes much faster, the ganglion cell does. And when I put it in the surround, it goes much slower.
Notice that when the light enters the surround region on this on-center ganglion cell, the level of activity recorded in the cell decreases. Conversely, a spot of light in the center of the receptive field increases the firing rate. A maximal response in an on-center ganglion cell is achieved when the entire center of the receptive field is illuminated. Likewise, if we illuminate only the surround with a ring of light, the ganglion cell is maximally inhibited. Note that if we illuminate both the center and surround region, the response is just above baseline. This occurs because center effects are slightly stronger than surround. Now let's look at the response of an off-center ganglion cell. To see what happens when a spot of light enters the receptive field, use the mouse to position the beam of light so that it falls on either the center or surround of the receptive field.
So if it's an off center, it turns it off and the light shines in the center and on when it's on the surround.
Notice that when the light enters the surround region of this off-center ganglion cell, the level of activity reported in the cell increases. Conversely, a spot of light in the center of the receptive field decreases the firing rate. If we illuminate the entire center of an off-center ganglion cell, the cell is maximally inhibited. A maximal response is achieved when the entire surround of the receptive field is illuminated. As with the on-center ganglion cell, if we illuminate both the center and surround region, the response changes very little from baseline. As you can see, uniform illumination of the visual field is less effective in activating a ganglion cell than is a well-placed small spot or a line or edge passing through the center of the cell's receptive field. This organization makes the ganglion cells sensitive to differences in the level of illumination across the receptive field, or what is called luminance contrast. To understand the importance of luminance contrast, use the mouse to drag the receptive field across the boundary between light and dark shown above. Note how the response rate changes depending on the position of the receptive field. By combining information from adjacent receptive fields, the brain can thus construct information about edges and ultimately shapes.
So activity is going way up as the center of the receptive field is close to the edge. As you can see, there's a suppression, then a much higher activation, and then another suppression as we go farther away.
This graph shows the responses of a hypothetical population of on-center ganglion cells whose receptive fields, labeled I to V, are distributed across a light-dark edge. Those cells whose activity is most effective have receptive fields whose center region lies adjacent to the light-dark edge. Thus, the information supplied by the retina to the brain does not give equal weight to all parts of the visual scene. Rather, it emphasizes features of the visual scene, such as boundaries and edges, that convey the most important information.
Okay.